Morning, ladies and gentlemen. I'll try and start with some announcements. Thank you for your work on Project 1. It was very good to see how smoothly most of you went through it. I know there were some cut-off PDFs and that. We're working on it. Those students will hear from us soon, but there weren't many of those. What I would love for you to do is, we gave you, fairly large sets of data and then some pretty small problems based on those data. But the data are there. And any of you that are interested, will come to me later and say, can I do some research on data science? You've got data. Do research. Research consists of asking questions. Mess around and ask questions. You have now lots of data sets, actually. And, some very small number of questions that we have addressed here, but mess around with them by all means. Homework. The lab deadline is at 7 p.m. on Fridays, just to make things sensible for everybody. The homework deadlines are all 7 p.m. instead of 5. Please be aware that office hours end at 5, and the GSIs are going to get up and leave at 5. They're not going to be there from 5 to 7 helping you with your homework, all right? So the idea is that you will come, if you are there at 5 o'clock, you will figure out more or less what you need to do, and then you have a couple of hours to breathe and get it done and submit it. Regrade requests are trickling in. There's a very small number, I'm happy to say, but now we have to get some process so that they don't trickle in all semester. And so all regrade requests for the past graded homeworks 1 through 4 are due this Friday at 7. When the midterm is, we are now beginning few-on-one tutoring, that is a few students with one GSI or one tutor. If you are interested in this, please contact your GSI directly. We'll get a collection. We'll see, what the need is. We'll see the availability of tutors, and the key is going to be matching schedules. And then we're going to try and get this done. This tutoring is not for help with homeworks, labs, and projects. It is for help with more general stuff. Like, I don't understand programming, or I don't get these concepts, right? Outside of the precise assignment, if you have more general issues, then these are good places to get them taken care of. A lot of this is going to be done by, opening up the textbook and saying, well, let's take a look at this example. What exactly happened here? And then addressing the question that you have. Okay, so those are my assignments. Do you have any administrative questions? Yes?
You said you were going to release some possible examples from midterm?
Yes. Okay, so this is all about the midterm. It's going to happen in just a moment. Any non-midterm questions? Yes. On Gradescope. Yeah, if you go to Gradescope, you log on, you should be able to see your homework, you should be able to see the rubric, you can see where your points were taken off, and there's a button for submitting a regrade request. We, try to be careful, and we don't agree to every regrade request, by no means. But, sometimes things happen. It's a big class. All right, so midterm, yes, I know, that's the burning question. What we are going to try and do is that by this Saturday, we will send you a bunch of stuff that you can start working on. I don't like to post problems for people to work on before we have covered the material. So the first thing that will go out to you is what we call the cheat sheet that you're going to get on your midterm, right? So the set of all, the coding and so on, to the extent that we think we should write it down and that you shouldn't have to remember. And then within the weekend, I hope that I will send you a set of problems to work on. And then there will be assorted sets done in lab. I will do a review of a combination of big stuff and exact and specific examples on Wednesday. So there'll be plenty of review materials for you to work on. We'll try to get a chunk of it out on Saturday, knowing that some people will want to work over the weekend. Our experience is that when the midterm is on Friday, Thursday tends to be a really big day. All right. More questions? So as I've said before, you don't have a computer on the midterm. By the way, you're currently doing a homework that has some probability calculations in it, yeah? And you've been given the option in some of those, you can do it exactly or you can do it by a simulation. I want you to be aware of two things. The big thing is that a simulation does not give you an exact answer. Right? So you may be satisfied with a simulation, but that's not an exact answer. And on the midterm, I'm going to be asking for exact answers. You won't have a computer to simulate with. So whatever you do on your homework, please make sure that you know how to get those exact answers. All clear? You should need no more than the rules of probability that we discussed in class, and there was a discussion worksheet that was done last lab. So they're not intended to be very difficult, but you do need to be able to work those out. So the questions on the exam are obviously going to be things that you can do without using a computer. Sometimes we're going to give you fill in the blanks in code. We're going to give you code and ask, is this going to run? We're going to say, could you write one line of code to do this, please? So very short coding questions, but a lot of, what's the chance that this happens? Here is a picture, and here's a bunch of descriptions. Which description matches this picture? And so on and so forth, that kind of thing. And a lot of concepts, was this a randomized controlled experiment? What can you conclude from this study, etc.? We're careful about those because you don't have much time. So we don't give you things that are very long to read and very long to write. But naturally, being the nature of the exam it's going to be more conceptual than coding. All right, time to get to work. I am going to summarize what we did last time. And actually, maybe the best thing to do is to start with just looking at the notebook from last time. So we had these data on jury panels in Alameda County, and there were about 1,500 people, which for reasons we discussed before, should be selected at random from an eligible population. The ACLU had data on the eligible population, the ethnic composition of that, and data on the panels. And we did a little analysis that showed that these panels really don't look like a random sample from here. Okay? And so the general, that type of analysis is called a goodness of fit analysis. Classically, I put it in quotes because I hate it. I don't even know that goodness is a word that should be used like that. Is that even English? Anyway, it's standard in the field, right? It's basically how well does the model fit the data. So what this is you're looking at a categorical sample. So our sample is a list of ethnicities. And we're trying to see if it is drawn from a known population, okay, at random. The key is it drawn randomly from something that you already know? And so the steps we took were, first we decided on a measure of the distance between two distributions. And what was that measure, please? A distribution here and a distribution there, and the measure was called total variation distance. And how does that go? I'm very patient. So I'll show you the data again. Might be easier to answer in that question, in that context. Go. So now what do I do? Yeah. Take the difference between each one of these categories. Some of those will be plus and some of those will be minus. You agree? If I add them all up, what will I get? 0. So what do? Absolute value, then add, divide by 2. Yes? Okay, that is a measure of distance between two distributions. Thank you. So that is your test statistic. A statistic is something that you compute based on the sample. And every time you want to make a decision like this, was it this way or that way? Was it a random sample or not? You have to come up with a statistic that kind of helps you make that decision. And so our distance measure was that. Having done that, yes. A statistic is a number. A statistic is one number calculated based on the sample. The question was, can a statistic be a table? So now we compute the statistic from the sample. So that is, you have our the total variation distance between the eligible distribution and the panel distribution came out to be 0.14. This is what we're going to call the observed value of our statistic. This 0.14 has a very important status. This is the actual difference that was observed. And now what we want to do is we want to compare with what a random sample would have given us. So this kind of decision making is always a mind game. If you had drawn the sample at random, what would you have got? And until a course like this, we had to tell students that by mathematical theory, it is known that you would have got something that looks like such and such, and they would have to take that part on faith. Now, we don't have to do that. You can actually see what you would have got by sampling over and over again from the population. Because the population is known, you can do that. And so what we did was we sampled over and over again and computed the statistic every time. And we ended up with that. And that was, how many repetitions did we have? We had 5,000 repetitions. No, this. That's where we were. We had 5,000 repetitions. That was our sample size. And so this histogram represents 5,000 total variation distances. Each one is the distance between a random sample and the population. These distances all seem to be in the range, well, they're distances, so they're going to be greater than 0. And they all seem to be in the range 0 to about, 0.05 or so. Ours was out here, which does not look at all like the distances that you typically get from a random sample. And therefore, our decision was clear. Our sample does not look like a random sample from that population, right? So now at this point, it is tempting to start jumping to conclusions. And what I'd like to do is now talk about the science in data science. You have a numerical calculation which gives you an answer. It is important now to assess what it means. In order to assess what it means, you have to understand the data very, very well, and that's nowhere in Python. That's in the description of what was actually done. And so one of the things I want to point out is how the samples were drawn and so on. So what we're going to do is we're going to forget all the calculations that we did, and we're just going to go back and understand these numbers. So these panels were 1,453 people on 11 jury panels. First to note, these were the 1,453 people who showed up for jury duty. More people were summoned. Some of those people didn't show up. So already what you are concluding is that the people who showed up for jury duty does not look like the distribution in the eligible population. Of course, there is some self-selection in who shows up and who doesn't. And one of the things to keep in mind is I did not know this until we did this example last year. So I looked we looked into what was going on, and the ACLU paper says something that is very relevant to us who are potential jurors in Alameda County. Alameda County does not have any system by which it goes after people who don't show up when they're summoned. You get that letter, it sits in the bottom of your junk mail, you forget to show up, you go, ooh, I've just broken the law. You kind of have, but nobody's coming after you. So this has an effect on people showing up or not. Other counties have a process. We do not yet, I don't think. We certainly didn't when this was done. So that's an important thing to note. Yes. The other thing that I would like to note is that these people, their ethnicities, somebody categorized them. And I looked quite hard at the ACLU paper to see, who got classified as black, who got classified as, was it self-reported, what was it? There is one statement that says the attorneys cooperated in collecting jury pool data. I don't actually know what that means. And so it would be worth going in to see exactly how that was done, and especially if it was self-reported. The connection between what each of those 1,453 people thought these labels mean compared to what this distribution of eligible jurors thinks those labels mean. Because there is not a unique definition of those labels. And how those labels are defined and who gets put into those labels have all kinds of social, cultural, political aspects that influence the data. So there is a murkiness there already. Are the classifications actually the same? Like when you're rolling a die, whether it's 1, 2, 3, 4, 5, 6, it's pretty evident. But these are not so clear, right? And also the parity is not so clear. And then finally, when you look here, these are eligible jurors. Where do you think that data came from? Eligible jurors in Alameda County. Where do you think that those data came from? Where would you look if you had to look? Census is where you would look, right? You would look for, there are distributions of ethnicity by age. So you would look for people aged 18 and over, and you would find a distribution of ethnicities. But are those the eligible jurors? What has to happen? They have to be A, U.S. citizen. Yep. Census not measuring that. A U.S. citizen. B, able to communicate in English. C, not convicted of felony, etc., etc., etc. That's not being kept track of. So those numbers themselves are estimates. There is a professor in, I think, San Diego State, who made these estimates, and they were accepted by the courts as being estimates, but he took into account the census data as well as estimates of all these other proportions. So there's some murk in that population of eligible, the distribution of eligible jurors to start with. And then there's a time issue. Do you remember a few weeks ago in this class we saw some data about the ethnic composition of California changing over the last decade or so? Like the percent of Hispanic children was rising quite a lot. Yep. These estimates were made in 2002 based on the 2000 census. This study is about 2010 jury panels. Things have changed. In Alameda County in particular, things have changed. Even if you use just the census numbers, they don't look like this, right? So there's a lot to think about before you start using these data to make policy. Now, the ACLU's report is very sensible. It says, look, whatever you're going to do, you should start going after people who don't show up, and you should avoid situations like wrong addresses for people, right? Undeliverable mail, right? That also disproportionately affects certain communities. So those basics need to be addressed. They're not asking for anything very dramatic or politically charged. They're just saying do the sensible things that will help improve matters. The reason I have spent so much time talking about this is to note that while we have this clean and beautiful calculation, and at the end of last lecture we all went, yep, not a random sample, and then felt terribly pleased with ourselves. At the end of this discussion we know, yeah, what do we actually know? We know that this distribution does not look like a random sample of this distribution. What that says about the juries is much more subtle and much more complex. So please understand that the numerical calculation only does so much. There's more sociological analysis that you have to do to figure out what exactly is happening and what should be done to address these issues. Okay? So when you analyze your own data, I hope you won't stop at the total variation distance. Go back and look at the data themselves and see where they came from. That is often very revealing. All right. So what I want to do today is to go through and give you some terminology. The way we made this decision, well, we have some data. We've got a measure of what we're trying to capture. Had the sample been random, it would have come out such and such way. Now let's compare. That is a specific instance of a very general statistical technique called testing hypotheses. And it is perhaps the most used technique, well, one of the two most used techniques of statistical inference anywhere in any subject. And so what we're going to do now in the context of another example is develop the terminology of the subject. And then after a couple of examples, hopefully we'll get to probabilities that we make a good decision or a bad decision. All right, so I'm going to stop for a second and take questions about what was discussed thus far. Well, I hope there will be questions at some future time. It's a lot to take in and think about. I've tried to write it out carefully. Go and take a look at the discussion in the text. There's lots of quotes from the ACLU report and from the Alameda County Superior Court as to how juries are selected. Yes? The conclusion is as good as the accuracy of the data, not just here but everywhere. Yes? What we are concluding is that this distribution doesn't look like a random sample of this distribution, right? But this distribution, the eligible jurors could be out to lunch, right? In which case we haven't learned anything. Now, it's probably not very far out to lunch, right? And it is, so there are always legal issues. It was accepted by the courts, right? And therefore, legal decisions are going to be made on that, right? So there is that. But yes, we have as thoughtful data scientists, we have to go back and see what is the next analysis that we should do. And I think, those estimates were made in 2002. It's time to make another set of estimates. So I think you can say qualitatively that if you have a more recent estimate, that will be more trustworthy. If you want to quantify that, you better start getting some recent estimates, right? You can't have a quantification of how much you're off without any basis on what the recent estimates are. So one good place for you to start might be to simply use the census figures. Right? So ignore the English language issue, the felony convictions and so on, which are considerable in some cases. But even if you ignore them from now, you will see that the distance comes out to be not quite as bad if you use 2010 figures, for example. But even those, of course, aren't quite right because you have to take into account all of this other stuff. And that's not easy to take into account. Right? Somebody has to do a very thorough survey irrespective of jury panels, to figure out what those proportions are. That's a stretch, not an arm. Okay. So I will start with some terminology, and let me actually take you through a slide on the terminology. Okay. So we are testing hypotheses, and a test of hypotheses, a decision is a decision to be made between two views of the world. So the first view was that the panel actually looks like a random sample drawn from the population, and the second was it does not look like a random sample drawn from the population. These two worldviews have names. That the sample was generated at random from that population. This is one hypothesis. It's called the null hypothesis. Null because nothing is going on other than chance variation. So this is the hypothesis that you come up with when you look at these columns and say, well, they're different. But could have happened by chance. That's that hypothesis, known as the null. And then genius terminology, the other one's called the alternative. There's something going on other than chance. There is a difference between these two that is marked from the purposes of calculation. The null hypothesis is a completely specified set of assumptions about randomness. It is drawn from this population at random in this way. You can do a simulation under the null hypothesis. The alternative hypothesis need not be any statement about randomness at all. In fact, in our case, the statement was specifically that it wasn't drawn at random. Okay, So to construct a test, you need a test statistic, and this is some number that helps you decide between the two hypotheses. And then we have the game that we played. We forget the actual data and we say, suppose the sample had in fact been drawn at random. Suppose the world were like this. Then what would the statistic have been? That's the mind game that we play. What the statistic might be if the null hypothesis were true, and that is right here. This is what the total variation distance might have been had you been drawing at random. So we can't get the exact probability distribution because there are far too many samples for us to get hold of. We get as many as we have patience for. And we know that that's a pretty good approximation. And then what we do is we compare what we have versus what the null hypothesis predicts. And so the way you reach a conclusion is you compare what you observed to this distribution whose histogram that you just drew. So we had a 0.14 here and a distribution that was sitting here. And we said not consistent. So there are two situations you can get. Your observed statistic, if it is not consistent with the distribution, then the two things are off. Your data and the null hypothesis don't agree, so your null hypothesis has to go. You're going to pick up the alternative. Right? So our data did not agree with predictions by random chance, so we said, no, not random chance, something else was going on. If the two are consistent, then if you have to pick between the null and the alternative, you'll go, you know what, I'll stick with the null. I don't have enough reason to get rid of it. Okay. Now, there's always this question of what exactly consistent means. And in our example, it was unambiguous. The observed statistic was very far away from the null distribution, so there was really no question. We're going to have to develop what consistent means in such a way that we can use it, forgive the pun, consistently across analyses. Okay, so you ready for a new example? The method that we have discussed works in any setting at all where you have some question about whether data was generated at random or not. And what I'm going to do today is talk about this person, Gregor Mendel. Gregor Mendel was a monk in Austria who is credited with the modern theory of genetics. And he did it by a Google Doodle. Well, actually, he bred lots and lots of pea plants. So that was Google acknowledging Gregor Mendel at some point. I forget exactly which year. He bred lots and lots of pea plants, and he looked at whether the seeds were smooth or wrinkled, whether they were green or yellow, whether the flowers were purple and white. And he, in his head, had this brilliant idea that there were these little we call them now genes, that are passed down, and there's one from each parent, and then there's a randomness in the matching, right? The randomness in the pairing, and depending on the pairing, the progeny come out with some characteristic or another. Now it just seems something that we completely accept, but somebody had to think of that idea first, and that was him. And so what I'd like to do is I would like to use some of his data and to decide whether his model was any good. So he had many models about many aspects of these plants, and we'll just do one of them. Okay, so he had many, many plants, tens of thousands of them. And here are data on plants that have purple and white flowers. And his model was, if you look at these plants, each plant is either purple flowering or white flowering. They don't have both colors. He had a genetic reason for believing that the purple to white ratio was 3:1. So 75% purple plants, 25% white flowering plants. and each plant independent of everything else. Right? So what happens with one, the color of the flowers for one plant does not affect the color of the flowers of the other. And that's what he believed based on his analyses. And I have Shishi Lua sitting in front of me, who is the genetics master here, and I'm talking about Mendel. Well, I cannot be accused of being overcautious. Okay. And so he had this model 3:1, and he wanted to test it against his data. All right? And so here are the data. That's what his model predicts. These are the actual plants, and now the question is, what does this look like this apart from random error, or is his model actually flawed? And so an interesting first thing to do is to figure out how many plants there were. And so what is this thing called? It's called flowers.column. No, I should look at that. So we had just under 1,000 plants, and the observed. So now our question is: does this distribution look like this one? Yes. Can you suggest a statistic? Go. Don't Google. Okay. Can get away from Google? Yes. So what you have done is you've computed this proportion. Yes? Do you want to use that as your statistic? Okay. So here is a suggestion that we can use. The point I'm trying to make is there isn't one correct answer to what I've just asked. There are numerous statistics that you could use, and it is your choice which you use. Some may be more sensible than others, but we can see. So the observed proportion will be... let's just do observed proportion of purple. So 705 by total plants. You agree? And I really need to look at this thing. Okay, so what we've observed is 75.8%, right? So this is roughly 76%, then this is 24% roughly, okay? Can you suggest to me one statistic that we could use to measure whether his model is doing well or not? What is the statistic we've used thus far in our previous example? Variation distance. Does that apply here? Okay, talk to your neighbor, figure it out. The question is very specific. Does the total variation distance apply as a statistic here? All right. That shouldn't take that long. If you had to compute the total variation distance, what would you do? You would take the 0.75 and subtract what? This mess, right? So let's just call it 0.76. Yes? You would take the 0.75 and subtract 0.76. You take the 0.25 and subtract 0.24. Yes? And then you take absolute value, add up, divide by 2. It's a perfectly valid statistic. You could do it. Yeah? The reason we're not going to do it is A, because we've done it before, and B, when you have just two categories, once you know the proportion in one category, the other one is determined, you don't get any new information from it. So this idea that we should just use this 76% somehow as our statistic seems like a good idea. Right? Now, we won't do quite that. What we will do is we will look at what our hypotheses are, which we haven't stated. The null hypothesis is simply that Mendel's model is good. Right, that these plants are like random draws from a 3:1 population of purple plants and white plants. The alternative is that the model is off. We're not saying in what way off. So we're not saying whether one group should be bigger or smaller than his prediction. And so what we will use as our statistic is, certainly it seems sensible to look at the observed proportion of purple and subtract off 0.75. You agree? How far it is from 0.75 is important, but you know what? We're going to calculate that distance without the sign. That's how far we are from 0.75. So for his particular sample, that was the distance from his predicted proportion. And now what are we going to do? Is that a big distance or a small distance? Ooh. People just answer small because it kind of looks like a small number. You can't answer small or big unless you have something to compare with. There's no absolute big or small. Right? So what should you compare with? Other statistics computed based on what? Random sampling. So we should draw at random. Right? And so our situation here is rather, we could use the proportion from distributions, etc., and so on, but our situation is rather simple. We are simply drawing from this array. You agree? And we are drawing at random with replacement from that array. What's a method? Random choice. So we are going to draw from this array 929 times. And we are going to look at the proportion of purple plants that we get. And that's going to be our new statistic. I want you to look at those 3 lines of code, please. And convince yourself that those are useful lines of code. np.random choice draws from an array these many times. Yes? What's total plants? 929. That's the number that he had. So we're just replicating his sample by drawing at random. And np.random choice will return what? What type of object do you get back? You get an array. It will have how many elements in it? 929 elements, each of which is going to be purple or white. So now you want to figure out the proportion purple in your new sample. Yep. So np.count non-zero counts the number of purple, division by the total length of the array gives you the proportion. Okay, let's see what we got. We got 0.7287, all right. We do it again. 0.74, we do it again. Okay, it's 0.759, etc., etc., etc. You know what we're going to do next. What are we going to do next? We're going to simulate, we're going to write a for loop. Yep. And so we're just going to collect all of this. I should just say that our statistic is going to be not this number here, but the distance from 0.75. Okay, so let's do our simulation. Okay, we're going to do 5,000 repetitions just because I made up that number off the top of my head. We are going to collect I don't like this name. I'm going to call it sampled statistics. And we're going to start with an empty array. We are going to run our simulation each time, and we are going to augment this array each time. With the oh no, actually I was fine. Sorry, excuse me. I'm just fussing with names. I shouldn't do that. Okay, what I am collecting in props are the proportions. We're just collecting the proportions purple. Okay. Then we have our observed statistic that we have computed before. Anybody remember what that was? It was right here. This guy. Right? That you should, if I could color it, bright blue or something, I would. It's actually different in status from everything else. That is the reality. That's our observed statistic. Sample statistics is the one that I wanted to create up on top, is I will take these proportions and I will convert them to distances from 0.75. I would like you to look at these 2 lines, please. Abs is operating on what quantity here? That's a number. Yes? So this thing is a number. What is props? It's an array, so this operation is subtracting 0.75 from every element of that array. Absolute value of that is returning an array. Sample statistics are an array. Yes? Of what length? 5,000. Not 929. Let's do that again. This is why I asked the question. You get one of these statistics for every repetition. The 929 is inside that repetition. That's how many you draw to calculate that statistic in the first place. So this is an array of length 5,000, and now I am counting, well, actually, let me just run this, and we'll look at what you get. Okay, so ignore that for now. Look at the histogram. What does the histogram represent? How many numbers does that histogram represent? 5,000. It's one distance computed from each of your 5,000 replications. Yep. And what I have done is I have this one that was 0.008888. That was right here. I plotted it as a big red splotch there. Right? So Mendel's model predicts that our statistics should look like that if his model's good. The observed value of our statistics sits here. What do you think? Is that consistent with his distribution, or is it inconsistent with his distribution? Looks pretty darn consistent to me. That number is sitting right in the heart of the distribution. Yep? So these data support his model. There are other questions that have been raised about Mendel's data and his model, but here, I mean, you look at this and you say, okay, the model looks pretty good. So what have we done that we hadn't done before? We now have language. Null hypothesis. Mendel's model is good, right? And the chance model is you're drawing at random with replacement from purple, 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 white. Alternative hypothesis. Mendel's model is not good. Test statistic. The observed proportion minus 0.75 absolute value. The main move. Simulate that test statistic under the null hypothesis. Assume that the model is good. Generate lots of samples. From each sample, compute the statistic. Draw the histogram. This is the empirical distribution of your test statistic. It's approximately the probabilities, the actual probabilities that the test statistic behaves in particular ways. Now compare with what you actually got. Okay? And so here again, the question of consistency, there's hardly any doubt about that. That red point just really does look consistent with that histogram. But of course, now you come into situations where what if the point had been here? Then what would I have done? Right? There's some point at which it looks consistent here, it kind of looks consistent here, and then by about here, we're starting to get a little worried. Yep? So there is this issue of what's consistent, and I'm going to tell you something that I'd like you to take in deeply. That is a subjective call. It is a matter of judgment. There is no way around it. I know students like to have rules, and not only students. Practitioners like to have rules, but the rules come from somewhere, and those somewhere are people's opinions. So let's talk a little bit about the rule. So I am going to... what is done is you look at your point and you look at all the area to the right of it. Okay? Now, area to the right of histogram, that is what? That's a, is that going to be a value of the statistic? It's going to be percent per something. What is that? Area represents what in a histogram? Percents, right? Or proportions, right? So what we're going to do is we are going to simply see, what was my thing called? Sample stats. How many of them were greater than or equal to, what did I call it? Observed statistic. Okay, So I need to change this because I am the opposite. This word is full and this word is abbreviated. Now this word is abbreviated and this word is full. Terrible. Okay, I should do something about that. Okay, so this will count how many of these statistics were greater than or equal to this number. And I'm going to look at that as a proportion of the number of data points here. And how many do I have? How many statistics do I have? I have 5,000, so that is what we were calling repetitions. You agree? Okay. So what you're saying is that 54% were on the right side of this point, and therefore 46% were on the left. And that's your quantification of this is right in the heart of the distribution. No matter where the point is, even if, let me just take this. Supposing the statistic had been here, all right? Then we would have been worrying about whether it's consistent or not. So how about 0.35? Look good? No, sorry, 0.035. Yes? I'm just going to pretend that the statistic had been here. I'm going to compute this tail out here. And so that proportion comes out to be 1 and a bit percent, right? And so now there's the question of, well, is that too far out in the tail or what? Well, what do you think? Okay, so there are 517 people in the class. There can be 517 different opinions, and those are all fine. It's up to you. And I know it's scary, but it's up to you. So when you report a result of a test like this, we ask that you please report your statistic, provide that picture, and say, in my view, this is consistent, or in my view, this is not consistent. Now, of course, there are people freaking out, especially those who have done AP Stats, which is a scourge, really, which I wish would go away. There are conventional cutoffs for what is small and what is very small, and so on. So there is a conventional cutoff that says that if this number is less than 5%, then you can call it small. Okay, fine. So if that number is less than 5%, then convention says you can call it small, and the result is called statistically significant. Don't write this down. I'll come and talk about it on Friday, and you can see that I already have an attitude. Yes? The reason I have an attitude is that it's important to know where that convention comes from. And that convention is used across the sciences, social sciences, natural sciences, everywhere. Like the 5% is set in stone, like it's Avogadro's constant. The 5% came from Sir Ronald Fisher writing a paper in which he said, I find it convenient to use 5% as a cutoff. There's a lot to say about this and more examples to work out, and look at those cutoffs and see about error probabilities. That's the business of Friday. I got your email.